In the first lecture on matrix method in geometrical optics, we have seen some of the introductory facts regarding this very interesting method. Now today we are going to start the basic concept of this matrix method in geometrical optics. And in this regard, first of all, we will see the concept of translation matrix, or you may also call it transfer matrix. So you can see, for your convenience, I have made the figure which will be required to discuss this translation matrix. But before discussing the concept of translation matrix, I would like to share with you that this is actually a very important concept, not only for the university examination, but you will find that the problems related to this translation matrix are asked, in fact, very frequently in the standard competitive examinations like civil service IAS examination and different state public service commission examination. So this is a very important concept, and you should definitely enjoy it. After this lecture, you will get the complete idea of this translation matrix, as I hope. So let us start to know what is this translation matrix and what is its use. So let us see this figure. You can see in this figure, actually I have shown a lens-like structure here. This is actually a cylindrically symmetric optical system. And this axis you can see in this figure Z, as I have told you earlier in the previous lecture. This is actually the axis of our cylindrically symmetric optical system. And I have also taken another axis, which is x-axis, which is perpendicular to this z-axis. In fact, in our discussion, we will consider the paraxial rays, and you know, paraxial rays means those rays which are very close to the axis of our optical system. So see this figure. In this figure, I have shown that this PQ is a paraxial ray, and for the discussion, I have considered 2 points on this paraxial ray. First one is point P and another is point M. And as you have learned in the previous lecture that we always define the coordinates of such a point to specify the ray. So corresponding to this point P, you can see that this at this point P, this ray makes an angle alpha 1 with the axis, that is z-axis, and this point is at a distance x1 from the axis. So in this condition, you simply say that this x1 alpha 1 is the coordinate of the ray, or optical coordinate you can say, at this point P. And similarly, at point M, this ray makes an angle alpha 2 with z-axis, and it is at a distance x2 from the axis. So the coordinates of this point M for the ray will be x2 alpha 2, as you can see here. Now since we consider a homogeneous medium, and when you will consider a homogeneous medium, you can see that the refractive index of the medium will not change. And if refractive index of the medium will not change, then the ray path will be a straight line. And if it means this PQ will be a straight line. And if it is a straight line, then it will be inclined at a particular angle to the axis. So in this condition, you can see this angle alpha 1 and alpha 2 will be same. And although alpha 1, alpha 2 will be same, but x1 will be not equal to x2. Again, you can see from this figure that corresponding to the point P and M on the ray, the point lying on the axis are actually P prime and M prime. So when you say that the ray moves from point P to M, then along the axis, its translation will be P prime M prime. And according to this figure, this P prime M prime, you can see this is equal to T. And this is actually known as translation of the ray. Translation of the ray. In fact, in this concept of translation matrix, our aim is to find a matrix which will transform the incident ray into the translated ray, or you can say, if we are given a particular ray defined by a matrix, then after that translation operation we can find the another ray. So how that will be find? For that, let us see first of all the geometry of this figure. You can see here that I have drawn a perpendicular Pn on this line mm prime. Mm prime is also perpendicular to the axis, so this angle at n will be 90 degree. And so from the geometry of figure, you can see here this pp prime is equal to x1 and mm prime is equal to x2. And when you will draw Pn perpendicular to mm prime, then you can see that this nm prime will be equal to pp prime. So this nm prime is nothing, this is simply x1, you can say. And if you want to find the value of x2, you can see the geometry of figure that this x2 will be equal to mm prime, and mm prime may be written as nm prime plus mn. Nm prime plus mn. But nm prime will be x1. For your convenience, actually I have written all those things here. You can see that this mm prime is equal to nm prime plus mn. But mm prime, as you have seen just now in the figure, this is x2, nm prime which is equal to pp prime, that is equal to x1. And to get the value of this mn, see the geometry of figure. Our aim is to find mn. So see the right angle triangle PMN. From this triangle, you can find the value of tan alpha 1. This angle is alpha 1, you can see here. And see the figure, tan alpha 1 will be what? That will be mn divided by pn. Mn by pn. But pn is equal to p prime m prime. So you can see this tan alpha 1 is mn divided by pn, and but pn is equal to p prime m prime. So it may be written as mn divided by p prime m prime. So from here you can see mn will be equal to p prime m prime tan alpha 1. But as you know, we are considering the paraxial rays, and paraxial ray means a ray which is very close to the axis of our optical system. And if it is very close to the optical axis of the optical system, then the angle made by the ray with the axis is very small. And since this angle alpha 1 is the angle made by the ray PQ with the axis of the optical system, that is z-axis, so this alpha 1 will be actually very small. And you know, if angle alpha 1 is very small, then tan alpha 1 is simply equal to alpha 1, because you have definitely studied in your calculus course that limit theta tends to 0, tan theta is equal to theta if theta is a radian measured angle. So from that formula you can say, since alpha 1 is very small, so tan alpha 1 may be simply written as alpha 1. So mn is equal to t alpha 1. So now substitute these values here. mm prime, you know this is x2, and nm prime you can see this is equal to pp prime, and that is equal to x1. So I have written here x1. And mn, you have calculated just now, this mn is equal to t times alpha 1. So at the place of mn you must write alpha 1 into t. So x2 is equal to x1 plus alpha 1 t. And let us say this is our equation number 1. Now, in the first lecture, that is introductory lecture on this concept, you have seen that instead of this coordinate alpha or alpha 1, we also use another coordinate which is actually known as optical direction cosine. Optical direction cosine, you can remember I have denoted that optical direction cosine by the symbol lambda. And how that optical direction cosine is defined, you have seen this, see this figure. If this angle is theta 1, then when you will multiply cos theta 1 by the refractive index, then that product of refractive index and cosine of this angle theta 1 is known as actually the optical direction cosine of the ray at this point P. So from the geometry of figure, now you can find it. So in terms of optical direction cosines at P, at point P, if you write the optical direction cosine at point P by the symbol lambda 1, then you have seen in the first lecture that this will be equal to n1 cos theta 1. But see the figure. In fact, you can see this theta 1 may be written as 90 minus alpha 1. So at the place of theta 1, we will write 90 minus alpha 1. So this is n1 cos 90 minus alpha 1. But cos 90 minus alpha 1 is sin alpha 1, so you may write it n1 sin alpha 1. But again you can see, since the ray is paraxial, alpha 1 is very small, and for a smaller angle sin alpha 1 will be also equal to alpha 1. So you can write this lambda 1 is simply equal to n1 into alpha 1, because due to the smaller value of alpha 1, this sin alpha 1 is also equal to alpha 1. Again you can see, if we want to define the optical direction cosine corresponding to the another point M of this on this ray, so corresponding to this point M, the angle theta is here theta 2 and alpha is alpha 2. So you can write again lambda 2. If we write the optical direction cosine corresponding to point M by the symbol lambda 2, that lambda 2 will be what? Refractive index of the medium at that point M, which I have written here n2, times cos theta 2. But according to the figure, just you have seen the figure, this theta 2 is equal to 90 minus alpha 2, and this will be equal to n2 sin alpha 2. But by the same reasoning, you can say this alpha 2 is very small, so sin alpha 2 will be simply equal to alpha 2, and therefore we can write lambda 2 is equal to n2 alpha 2, and say this is equation 3. But as you know, our medium is homogeneous. Our assumption is that medium is homogeneous, and so in this case this n1 n2 will be same, and alpha 1 and alpha 2 are also same, as the medium is homogeneous. Medium is homogeneous. So you know, in this case refractive index will be uniform, will be constant, so n1 will be equal to n2, and ray will be straight, and so the angle of inclination of this ray PQ with the axis will be everywhere same, and so alpha 1 is also equal to alpha 2. So from this these two equations 2 and 3, you can see, since n1 is equal to n2, alpha 1 is equal to alpha 2, so you can easily say that lambda 2 will be equal to lambda 1. Therefore we can say that lambda 2 is equal to lambda 1. Lambda 2 equal to lambda 1. Or equivalently you may write it in this manner. This is 0 into x1 plus 1 into lambda 1. Why actually I have written in this form, you will just understand after the next step. Why I have written this lambda 1 like 0 into x1 plus 1 into lambda 1. What's the reason behind it, you will see after this step. Let us see. Now you can find the value of x2 from this equation 1 by replacing this alpha 1 in terms of lambda 1. So see this equation 2. From equation 2 you can find the value of alpha 1. What will be alpha 1 from here? You see this is simply lambda 1 divided by n1. Now let us use this value of alpha 1 in this equation 1. It means at the place of alpha 1 we will write simply lambda 1 by n1. So using this in equation 1 we get, after this result, after the use of this result, what will be our equation 1? You can see equation 1 is x2 equal to, see here, x1 plus alpha 1 t, but instead of this alpha 1 now we will write lambda 1 by n1. So you can write t over n1 times lambda 1. Now you can understand why in this equation 4 I have written this lambda 1 in this form, that is 0 times x1 plus 1 times lambda 1. You can see this equation 5. Here actually x2 is one of the coordinates of point M of the ray, and lambda 2 is another coordinate of that point M for the ray. And so for the analogy of this equation 5, equation 4 has been written in this form, because you can compare when there is x1 RHS, here is also x1, when there is lambda 1, then here is also lambda 1. So with the analogy of equation 5 I have written this equation 4 in this form. Now you know the matrix algebra. Actually these two equations 4 and 5 may be written in a in a single equation by the use of matrix, or you can say in matrix form these equations 4 and 5 may be presented by a single equation. And how that can be written, you can easily understand it. So you can see the two equations, what are equation number 4 and 5? Two equations 4 and 5 can be written in matrix form. Matrix form as, see here, we will write a column matrix lambda 2x2 in LHS, and that will be equal to see the coefficient of this x1 in equation 5 is 1, and that and in equation 4 the coefficient of x1 is 0. So first of all write the coefficient of x1 here, and again see the coefficient of lambda 1 in equation 5 is t over n1, and that in equation 4 the coefficient of lambda 1 is 1. So you can write t over n1 and 1, and operate this matrix on lambda 1 x1. You can check it. This is actually a very important result, and I hope you know the matrix multiplication. If you will, if you want to find this lambda 2, I am just give a rough estimation of it. If you find lambda 2, what will be lambda 2? See here, lambda 2 will be equal to 1 into lambda 1, that is 1 into lambda 1 plus 0 into x1 plus 0 into x1, and that will be simply equal to lambda 1. And this is nothing, this is your equation number 4, you can see. And if you want to find the value of x2, you can see x2 will be what? X2 will be t over n1 times lambda 1. So this will be t by n1 into lambda 1, t by n1 into lambda 1 plus 1 into x1, 1 into x1. You know the matrix multiplication. So you can see this is nothing, this is simply our equation 5. So you can see this matrix equation A represents both of these equations, that is equation 4 and equation 5. So I have told you that these two equations 4 and 5 may be expressed in matrix form by a single equation. So this single equation actually represents those two equations. Actually here the column matrices lambda 2 x2 and this lambda 1 x1 may be looked upon as the rays at P and at M. Lambda 2 x2 represents the ray at ray at M, and this represents the ray at P. Lambda 1 x1 represents the ray at P, and lambda 2 x2 the ray at M. See the figure. Corresponding to this point P, the coordinates are lambda 1 x1 and corresponding to this point the coordinates are lambda 2 x2. So you can say that this lambda 1 x1. This is just a column matrix and it represents ray at P, and the another column matrix lambda 2 x2, this represents ray at M, you can see. So you can see this 2 by 2 matrix, which is matrix 1 0 T over N1 1, this is a 2 by 2 matrix. So this 2 by 2 matrix may be just taken as an operator. You know, matrix is just an operator, and when this operator is operated on this vector lambda 1 x1, you may also call it a vector. Lambda 1 x1 may be called a column vector, lambda 2 x2 is also a column vector. And so when this operator is operated on this vector lambda 1 x1, that operator changed this lambda 1 x1 into lambda 2 x2. So this is just the effect of translation or the process of translation over a distance t, you can see. So you can say the effect of translation, over a distance. Here actually ray is neither reflecting nor refracting, it is only translating from one point to another. So this is just an effect of translation over a distance t in a medium of refractive index n1 is given by a 2 by 2 matrix, and we will denote this 2 by 2 matrix by the symbol capital T, and this is defined as what? You can see this is your translation matrix here. So this is 1 0 T over N1 1. This is 1 0 T over N1 1. And this is our translation matrix. And you can see the effect of this translation matrix is what? Its effect is just to transform the ray lambda 1 x1 into the ray lambda 2 x2. So this lambda 1 x1 is represents a ray at P, and lambda 2 x2 represents the ray at M. And this translation matrix actually transforms the ray lambda 1 x1 into the ray lambda 2 x2 during the translation T in a homogeneous medium of refractive index N1. And that's why this is known as a translation matrix. So you can say the matrix T defined in equation B is just an operator. This is just an operator which transforms the ray lambda 1 x1. Mark it. Here the light ray has been represented by a column matrix This is just a mathematical representation. You may enjoy it. This light ray is represented by this column matrix lambda 1 x1, and this 2 by 2 matrix defined in equation B is just an operator, and this operator when operated on this column matrix lambda 1 x1, which represents a light ray, then this light ray lambda 1 x1 will be transformed into another light ray lambda 2 x2. So I have written here that matrix T defined in this equation B is just an operator which transforms the ray lambda 1 x1 into the ray lambda 2 x2, and that lambda 2 x2 during translation through T in a homogeneous medium. This translation matrix, this matrix defined in B, which actually transforms the ray lambda 1 x1 to the ray lambda 2 x2 after a translation T through in a homogeneous medium. Such a 2 by 2 matrix is known as translation matrix, or it is also called transfer matrix. So this T is known as translation or transfer matrix. So what is a translation matrix or transfer matrix? I hope you have understand. But one thing you should note, after getting this concept of transfer matrix, you must remember this expression for it, because when you will solve the numerical problems, you have to write this matrix expression directly, and also in the discussion of different theories related to this. So remember this equation B, that translation matrix is defined in this manner, that T equal to 1, a 2 by 2 matrix 1 0, T over n1 1. Now after knowing about this translation matrix, let us see two important facts regarding this translation matrix, and that two important facts will be invariably used in this theory. Two important facts regarding this translation matrix. First of all, see, if you will find the determinant of this translation matrix, you will see that this will be actually equal to 1. So see the first important point. Sorry, there is just a pen problem again. You have seen earlier too, but now it is okay. You can enjoy the lecture. So the first important fact, as I have told you, when you will find the determinant of this translation matrix, you will find that is simply equal to 1. So determinant T, what will be this? You can see, as our translation matrix is defined in B, you can see the determinant of this matrix will be determinant of 1 0 T over n1 1, and you can see this will be what? 1 times 1 1, and multiply this and this, you know the how this determinant will be solved. So this will be 1 minus 0, and that will be simply equal to 0. So determinant of this translation matrix is equal to 1. Now let us see the another important and interesting point here. As you have seen, there is 2 point. First point is first point was p prime. First point was in fact p prime corresponding to this point p on the ray, and another point was m prime corresponding to the point m on the ray. You have seen just now, and the gap between these 2 points or separation between these 2 points is t. Now let us divide this gap between these 2 points in 2 parts. Let us consider here there is a point, and this point and this distance is equal to t1, and this distance is equal to t2. It means we have divided the space or the gap between these 2 points in 2 parts, and the width of the first part is t1 and that of second part is t2. In fact, in this condition, if you consider that the refractive index of this part n1 and this part n2 are not different, we are again considering that medium is homogeneous, then actually this n1 will be equal to n2, and you can say this is equal to n. n1 and n2 both are same, and that is equal to n. In fact, in this condition, when the ray will travel through this medium, then we can define two translation matrices or two successive translation matrices for the gap of width t1 and that of width t2. So you can say if the gap t be divided, actually division may be made in several numbers, but for simplicity I have considered that this gap has been divided in 2 parts. The gap t be divided into 2 adjacent gaps t1 and t2. Let us say having indices n1 equal to n2 and this equal to n. Let us say then we get two successive translation matrices. And if you denote this translation matrices by the symbol t1 and t2, what will be t1? You can see this t1 will be on the basis of this definition. You can write t1. This will be 1, 0 and t1 over n and 1, because n1 is equal to n2, and when we will define t2, this will be what? On the basis of same equation you can write this is matrix 1, 0 and t2 over n 1. t2 over 1. Now you can check a very important fact. When you will take the product of these translation matrices t1 and t2 or t2 and t1, you will see that t1 times t2 and t2 times t1 will be same. It means the product of these translation matrices is commutative, and what will be that? You can easily find it. You can see what will be the result. Then you can check it yourself by taking the product T1 times T2. Find T1 times T2 and also T2 times T1. You will see these two products will be same. And what will be these two products? You can easily see. You have to multiply this matrix by this matrix, and I know you know the technique of matrix multiplication. This is a very simple matrix because this is 2 by 2, so you can easily find the product. So I am just writing the product here directly. You can see this will be 1 0 and T1 plus T2 over n and 1. Or you can say if these products of T1 and the product of T1 and T2 or T2 and T1, if you denote it by the symbol T, then this T will be equal to what? This is 1 0, and this T1 plus T2 in general may be written as summation over Ti divided by n and 1. As I have told you earlier that I have divided the gap between those 2 points in 2 parts having width T1 and T2, but if you divide that space or that gap in several parts, then in similar manner you will get the result at the place of T1 plus T2. You will get T1 plus T2 plus T3 and so on. So in general you can write here summation over Ti. Summation over Ti. So in this way you can say that all the translation matrices can be multiplied to produce a single matrix for the effect of whole gap. So this is the technique. So finally you can say all the translational matrices can be multiplied to produce a single matrix for the effect of the whole gap. So I hope you have understand the concept of this translation matrix. Actually this is a very useful concept, and you will see its utility after getting the theoretical aspect in forthcoming lectures.